In biology, as in physics, there's something very curious that happens, that if you keep asking why, something interesting goes on. I'll give you two examples. First of all, imagine cicadas. So the cicadas come out at 13 years and 17 years. Okay. And so if you're a biologist and you say, so why is that? And then you get this explanation for, well, it's because they're trying to be off cycle from their predators. Because if it was 12 years, then every 2 year, every 3 year, every 4 year, every 6 year predator would eat you when you come out, right? So, and you say, okay, cool. That makes sense. What's special about 13 and 17? Oh, they're prime. And why are they prime? Well, now you're in the math department. You're no longer in the biology department. You're no longer in the physics department. You're now in the math department to understand why the distribution of primes is what it is. Another example, and I'm not a physicist, but what I see is every time you talk to a physicist and you say, hey, why do the, leptons do this or that, or the fermions are doing whatever? Eventually the answer is, oh, because there's this mathematical, this SU8 group or whatever the heck it is, and it has certain symmetries and these certain structures. Yeah, great. Once again, you're in the math department. So something interesting happens is that there are facts that you come across. Many of them are very surprising. You don't get to design them. You get more out than you put in a certain way, because you make very minimal assumptions, and then certain facts are thrust upon you. For example, the value of Feigenbaum's constant, the value of natural logarithm E. These things you sort of discover, right? And the salient fact is this: if those facts were different, then biology and physics would be different, right? So they matter. They impact instructively, functionally, they impact the physical world. If the distribution of primes was something else, well, then the cicadas would have been coming out at different times. But the reverse isn't true. What I mean is, there is nothing you can do in the physical world to change E, as far as I know, to change E or to change Feigenbaum's constant. You could have swapped out all the constants at the Big Bang, right? You can change all the different things. You are not going to change those things. So this, I think, Plato and Pythagoras understood very clearly, that there is a set of truths which impact the physical world, but they themselves are not defined by and determined by what happens in the physical world. You can't change them by things you do in the physical world, right? And so I'll make a couple claims about that. One claim is, I think we call physics those things that are constrained by those patterns. When you say, hey, why is this the way it is? It's because this is how symmetries or topology or whatever. Biology are the things that are enabled by those. They're free lunches. Their biology exploits these kinds of truths. And really, it enables biology and evolution to do amazing things without having to pay for it. I think there's a lot of free lunches going on here. And so I show you a Xenobot or an Anthrobot, and I say, hey, look, here are some amazing things they're doing that tissue has never done before in their history. You say, first of all, where did that come from? And when did we pay the computational cost for it? Because we know when we paid the computational cost to design a frog or a human, it was for the eons that the genome was bashing against the environment getting selected, right? So we paid the computational cost of that. There's never been any Anthrobots. There's never been any Xenobots. When did we pay the computational cost for designing kinematic self-replication and, all these things that they're able to do? So there's two things people say. One is, well, it's sort of, you got it at the same time that they were being selected to be good humans and good frogs. Now, the problem with that is it kind of undermines the point of evolution. The point of evolutionary theory was to have a very tight specificity between how you are now and the history of selection that got you here, right? The history of environments that got you to this point. If you say, yeah, okay, so this is what your environmental history was, and by the way, you got something completely different. You got these other skills that you didn't know about. That's really strange, right? And so then what people say is, well, it's emergent. And they say, what's that? What does that mean? And they say, well, besides the fact that you got surprised, right? Emergence is often just means I didn't see it coming. There was something happened. I didn't know that was going to happen. So they say, what does it mean that it's emergent? And people say, well, and there are many emergent things like this. For example, the fact that gene regulatory networks can do associative learning. Like, that's amazing. And you don't need evolution for that. Even random genetic regulatory networks can do associative learning. I say, why does that happen? And they say, well, it's just a fact that holds in the world. Just a fact that holds. So now you have an option. And you can go one of two ways. You can either say, okay, look, I like my sparse ontology. I don't want to think about weird Platonic spaces. I'm a physicalist. I want the physical world, nothing more. So what we're going to do is when we come across these crazy things that are very specific, like, anthrobots have 4 specific behaviors that they switch around. Why 4? Why not 12? Why not 1? Like 4? Why 4? When we come across these things, just like when we come across the value of E or Feigenbaum's number or whatever, what we're going to do is we're going to write it down in our big book of emergence, and that's it. We're just gonna have to live with it. This is what happens. We're just, there's some cool surprises. When we come across them, we're gonna write them down. Great. It's a random grab bag of stuff, and when we come across them, we'll write them down. That's one. The upside is you get to be a physicalist, and you get to keep your sparse ontology. The downside is I find it incredibly pessimistic and Mysterian, because you're basically then just willing to make a catalog of these amazing patterns. Why not instead? And this is why I started with this Platonic terminology. Why not do what the mathematicians already do? A huge number of them say, we are going to make the same optimistic assumption that science makes, that there's an underlying structure to that latent space. It's not a random grab bag of stuff. There's a space to it where these patterns come from. And by studying them systematically, we can get from one to another. We can map out the space. We can find out the relationships between them. We can get an idea of what's in that space. And we're not going to assume that it's just random. We're going to assume there's some kind of structure to it. And you'll see all kinds of people, well-known mathematicians that talk about this stuff, Penrose and lots of other people who will say that, yeah, there's another space physically, and it has spatial structure, it has components to it, and so on. We can traverse that space in various ways, and then there's the physical space. So I find that much more appealing, because it suggests a research program, which we are now undergoing in our lab.